In this lecture series, we will understand interpolation, which is a numerical technique. It's used to find out the value of a function at certain unknown variable x. When do we need this? It's because often the behavior of the system is not given in the form of in a functional form. Rather, it is provided in the form of a data, and which comes out of an experiment, and where you perform the experiment and find out the behavior of the system at certain variable x for specific values of the variable x. And now, for some reason, you need to know the behavior of the system at a certain x, where you have not, for that variable, if you have not performed the experiment. In that case, this technique, interpolation technique, or we can see about extrapolation also, that is a technique which comes handy, and most of the time that will be very helpful. So if you want to look out what is the typical experiment, so let us say an example. For example, let us see the results data gathered from an experiment, which is a neutron scattering experiment. I am not going into the detail of the experiment. So this is the experimental values collected for the scattering cross section corresponding to different neutron energies. So, and this is the error bar. So this is the energy of the neutron, and this is the cross section. And suppose if I try to plot these two, so how they look like is, so this is how the data point looks like, and here this is energy and this is a cross section. So if you see, you can say this has some functional form which I was not knowing. I have only the data value. And suppose for my study I need the value of the cross section at certain energy at which I have not performed this experiment. So for instance, for example, if I want to know the behavior of the system at 85 MeV, where I have not performed the experiment, because rather I performed the experiment with the increment of 25 and I skipped 85. So this is the one case where you can, as an example I am showing, where you may need to use interpolation to find out the cross section at certain x where you don't have the data. In short, what we have is, we are having a variable x and a behavior of a system which is f of x, which is an unknown function. I don't know about what f of x is. Rather, what I know is, I know for x0 the function value is f0, x1, f1, x2, f2, it go on maybe up to xn, fn, and this is f of x0, that's the behavior of the function at x equal to x0, and this is at x equal to x1, f of x2, f of xn. So we have this data, and now I want to find out the behavior of the system, say at certain x star, let me call it, and the x star is not equal to xi, where I equal to 0 to n. So in that case, x star may not, if I have not performed the experiment in the x star, and if I want to know what is the behavior of my system or the function at x star. When you put up such a question, this can be divided into two types. So one, we call it as an interpolation. What do we mean by interpolation is, when your x star lies between x0 and x1, provided we have represented this in ascending order, if it falls between x0 and xn, then that problem is called as your interpolation. That is what, when x star is less than xn but greater than x0. So this problem is called as your interpolation. Often interpolation problems are easy to solve because more or less the behavior of the system is very well constrained by the neighboring points. On the other hand, if your x star doesn't fall in this range, rather it falls outside this range, that problem you call it as extrapolation. That is, when x star is greater than xn or x star is less than x0. Extrapolation problems are usually complicated, complex, may not be able to provide the functional form correctly because they falls outside the range and we never know how the function behaves when the x is changing. X is being out of the range of experiment what you have done. So if I represent this in a graphical form, what we have is so let me plot this as x and this as f of x. So, and we have the collection of data, say something like 1, 2, 3, 4, 5, 6. Suppose we have 6 data. So now interpolation happens when this is what your this is your x0 and let us call this as your xn, where n equal to, in our case, n equal to 6. So when your x star falls in between this range, you call that as an interpolation. When the x star falls outside this range, you call that as an extrapolation. Fine. So, and often extrapolation can be erroneous because we never know what is going to be the behavior of the system beyond this data point. It may not be connected by a smooth curve. It may fall down or may go spike. It may sharply increase or those things. We never know. So often extrapolation is very erroneous. Interpolation, to an extent, we can try to estimate it. So when we come to interpolation, there are two common techniques are used. The first one is what we call as a polynomial interpolation. And what we do in a polynomial interpolation is we use the property any smoothly varying function which is not known. Any smoothly varying function can be represented by a polynomial of, say, a degree n. Okay. So, and may not be exactly represented, but closely. Any smoothly varying function can be closely represented by a polynomial of degree n, and n can be a much large or small, whatever it is, that we will see it later. So we will use that property to construct a polynomial which is going to pass through all these points and use that polynomial to find the value, say some unknown value at some x star. And this is the technique which is used for polynomial interpolation. And now a polynomial interpolation can also be used if I try to extend this polynomial beyond this point, and if you assume the behavior of the system is still maintained by the polynomial even outside this range, then you can use this polynomial interpolation for the extrapolation also. So this is one of the very simple and very elegant method by which you can interpolate the function at certain unknown x. Okay, often this may not be exact because we never know in between these ranges whether the function can be described by the polynomial, we are assuming. So, however, in interpolation we can still, considering the neighboring points, if the data points are close by, then you can still use it. But however, when it comes to extrapolation, this can be largely erroneous. And this is one of the simple method. Yet there is another method, which is a very powerful method for interpolation, which we call as a spline interpolation. And the spline interpolation is an age-old technique humans were using. So, and okay, if I want to put it in a simple way, if you remember in a childhood days, we must have solved a puzzle of connecting dots. So there will be a dots will be given and you just connect it. So, and if you try to connect the dots, what will come out is a elephant or an apple or something. We have a kind of similar thing. That's the point. A kind of similarity to that is what we spline interpolation. What we do is, if a kid is smart, so what the kid doesn't just straight connect the point, it tries to smoothen the curve. It doesn't make any discontinuity along the point. You try to make smooth the curve so that the figure looks more more good looking because there is no discontinuities. So the breaks and all, so it's smoothly connect. So, and this was a technique humans were actually using for age long to interpolate the values in between the data. So they don't, how they use it is, they use it, how they do it is they use spline. What do you mean by spline? Spline is a flexible strip. They try to connect the neighboring points, maybe some 3 points or 4 points, using a flexible strip, join the points, and then they draw the line, and then they connect the next 3 points, and then they join the line, and then they connect the next 3 points, then they join the line. So that way they provide a they smoothly connect all the data points and use the line to predict the values unknown x values. So, and mathematical analogy of this technique is what we call as a spline interpolation. And this is very powerful because it doesn't bother about the behavior of the system at faraway places. It is because here what happened, when the moment I try to interpolate using a polynomial, the value of this behavior of the system at this x depends upon the value at faraway x also. That may not be, my system wouldn't bother that. So rather here we don't have to bother about these points because it takes only the neighboring points, and that's how this will be more powerful and more smoother. Many times it's better than this. We have some demo examples where I can show this will fail and where this will work fantastic. Fine. And okay, so now if you see here, so this technique, you can't use this technique to extrapolate. You can't extend it further because of course we are not having a polynomial. Here we are having a polynomial, we can extend it. Here we can't extend it. So this spline interpolation cannot be used for extrapolation. So rather this can be used only for the interpolation. So that's how even the spline techniques are often very robust and better techniques. Sometimes you may have to stick to polynomial interpolation because if you wanted to, your problem which you are handling which needs extrapolation also, and polynomial is the only way where you can get an idea about the extrapolation beyond it. However, you are not supposed to go, you are extrapolating, you should not extrapolate as much far away from your ranges, rather you should be closer to that. So this is the two techniques which is being used for interpolation, to interpolating the function at some unknown variable x. So now let us first concentrate on this method, that is a polynomial interpolation or extrapolation, and then we will slowly go next to the spline interpolation. So let us start with the polynomial interpolation. What we do in a polynomial interpolation is we are given a set of data where x and f of x, so where f of x functional form is not known, we have x0, x1, x2, maybe something around xn, and we are having the function dependence is the behavior of the function at x0 is equal to f0, f1, f2 and up to fn, which is nothing but f of x0, f of x1, f of x2 to f of xn. Well, so now in the polynomial interpolation, so what we are trying to do is we are in the graphical form. So we have these points. So this is x, f of x, and we have these points, say some points we have, and we try to construct the polynomial. Okay, so if you want to see what is a polynomial can be written. And so I am going to approximate this behavior of the system in terms of a polynomial f of x, which is nothing but I equal to 0 to say some nth degree polynomial I am going to do into a of I, x of x to the power of I, where a of I is the coefficients. So if you see this carefully, so this is a polynomial I have to construct so that I can use this polynomial to find out the behavior of the function at certain unknown value. Fine. So, and if you see, to construct the polynomial, one quantity which I need to know is this ai. That's the coefficients. So, and these coefficients are the unknowns. So now if I have a nth order polynomial, then I have n unknowns, n plus, okay, 0 to n means n plus 1. If I have a, 0 to n, then I have a n plus 1 unknowns. So now, so for example, so when I have a n plus 1 unknowns, I need at least that many points. Or invert, if I have 1, 2, 3, 4, 5, 6. If I have 6 points, and if I want to express in terms of a polynomial, what I can do is, I will write my polynomial as f of x equal to a0 plus a1x plus a2x square plus a3x cube plus a4 x power 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. A power 5, x power 5. So now we have total 5 unknowns, 6 unknowns. 1, 2, 3, 4, 5, and 6. So I can use the 6 points to estimate all these unknowns, and that's how we can construct a polynomial. So we won't do it in this technique, rather we have a more smart way of finding out the polynomials that we will look into it. And how we are going to, so in principle, so if I have n points, or if I start from 0, if I have n plus 1 data points, so if you have n plus 1 data points, data values, data set I would say, set, the maximum degree of the polynomial what you can construct will be nth degree polynomial. We can't go beyond that, because then the unknowns become larger than your given information. We will not be able to solve this. So this is what, so given a n plus 1 data point, what we can do is we can construct a polynomial whose degree is n. So this is what, how we are going to construct the polynomial. Of course, there are many algorithms, very smart and efficient algorithm that we will see it one by one. So for the first we will see about a very simple algorithm, and it's a very elegant algorithm, rather simple algorithm. That is what you call as your Newton forward difference. What we see in a Newton forward difference is, if suppose you have the data set, if this data set are evenly spaced, that means if my xi plus 1 minus xi, the difference between these two, any of this always constant, and if I call that as h, then we can use this technique, Newton forward difference, to find out the value of the function at a certain unknown x, that is x star, whatever we call it. Okay, so how we are going to construct this polynomial? So when your data values are evenly spaced, so we will define a forward difference operator, that is, so delta f of I equal to f of I plus 1 minus f of I, and we can proceed further, something like del square f of I will be equal to del f of I plus 1 minus delta f of I. So this is a forward difference operator delta, which I am using to I'm using that operator to find out the difference between those two data sets. So I can keep going on, maybe say something del of k f of I will be equal to del of k minus 1 f of I plus 1 minus delta f of I. So now if you see, I can, if I define an operator, such an forward difference operator, which is nothing but the difference between f of 1 minus f of 0, f of 2 minus f of 1, f of 3 minus f of 2, and then I keep on doing the difference again. So there's a that is an forward difference operator I defined. So then we can do a bit of jugglery. So if I from here, if I write delta f of 0 will be f of 1 minus f of 0. So from here I can write f of 1 equal to f of 0 plus delta f of 0, and that will be equal to delta plus 1 to the power of f of, or sorry, I will write it like this, that is better. So 1 plus delta power of f of 0. Fine. And okay, let me go for delta f of 1. Delta f of 1 will be equal to f of 2 minus f of 1. So this will become therefore f of 2 is equal to the same way 1 plus delta f of 1, and if I substitute for this f of 1, what you are going to get is 1 plus delta square of f of 1. Similarly, you can keep on doing that, and what you will find is f of 3 will be 1 plus delta cube of f of 0, and you keep doing that, and finally we can find out maybe certain f of k will be equal to 1 plus delta to the power of k of f of 0. So now then we take out this f of k. What is f of k? Our f of k is nothing but f of x of k. That's what you mentioned. K can be anything between 0, 1, 2, 3, 3, and whatever the value we have, that can be any k. So this is equal to what we found is, since we defined this forward difference operator, so this will be 1 plus delta to the power of k of f0. And now let us expand this as a binomial series. So when we expand this in a binomial series is not an infinite series. It truncates when that okay, let me write it down, you will understand it. So what happens? So this will be what? When I expand this in binomial series, what we have is f0 plus delta f0 by what is that? By 1 factorial into k plus delta square f0 by 2 factorial k into k minus 1 plus let me write down here delta cube of f0 is a third difference of 3 factorial k into k minus 1 k minus 2 plus go on, and there may be a certain for the n, if I want right up to the n, what we have, so delta power n f0 divided by n factorial into k minus 1 k minus 2, it goes on, the product will stop at k minus n minus 1. Okay, so we can see for example that when the k equal to 1, so this goes to 0, so it stops here. When k equal to 2, this goes to 0, so it stops here. So this is not an infinite series. It truncates whenever the term becomes equal to k. The number of terms becomes equal to the k value, then that time this beyond that the series doesn't exist, so it is not an infinite series, it truncates. Fine. And so now, okay, let us try to find what this k is, f of k is. So, and what will be the k? So k is something like x of k. The k can be 0, 1, 2, 3 up to anything else. So then I can write x of k is equal to, starting from x0 plus k into h, where h is the difference between xi and 1. So x0 equal to k into xh. So this will let me write k equal to xk minus x0 divided by h. So now let me substitute this k here. So, and if I want to write, I substitute the value of k everywhere, and I want to take this h commonly outside. So since there is a minus 1, so minus 1, minus 2 and all, so what we will get is f of xk will be equal to f0 plus delta f0, and there's only one k is there. I'm going to take the h outside, h1 factorial, and this will be xk minus x0 plus del square f0. Now I'm going to take 2k, so I'll take both the h outside, so that becomes h square 2 factorial, and this will be xk minus x0 into xk minus x0 minus 1 will become h, since I taken the h commonly outside, and then plus third one will be del cube f0, and here are 3 terms. I will get 3h outside, so this will become h cube 3 factorial, and this will be k will become xk minus x0, xk minus x0 minus h, then this will be xk minus x0 minus 2h plus 1, and the last term will be, let us write over the nth term, that will be plus delta power n f of 0. Again we have n h terms will come out, so it becomes h power n factorial, and this will be what? Xk minus x0, xk minus x0 minus h, and this product goes on, and finally it stops here. So what we have is xk minus x0 minus n minus 1 h. Okay, so this is a very interesting expression. So why this is interesting is, so we have constructed this is going to be valid for all k's. In fact, if you see, the moment I put xk equal to k equal to 0, if you can see here, so if I put k equal to 0, so what am I going to get? F of this will become f0, because these terms all will goes to 0. So when k equal to 0, what you're going to get is f0. That means that's what the point, when x is equal to 0, f0. And now I want you to try that. You put k equal to 1. So what you will find is this term k equal to 1, when you put up the term, all the other terms will vanish. What you'll get is when k becomes 1, this is become f of 1 from the forward operator formula. You will get it. So that means what we have done is, so this is a function. So this is a function which satisfy all the points given by our data. So that means, so this is a function which satisfies all the points. So now, so since it satisfies all the point, if I remove this xk, and instead of xk, I will write an arbitrary x, which I don't know, as a variable. The moment I remove this k and I write it as a x, so the moment I write it as an x, so then this becomes a polynomial, because you can see here, this will be for n plus 1 data point. This is going to be the nth degree polynomial, because all the product when you add up is going to become an nth degree polynomial. Not just that, this nth degree polynomial is going to pass through all the points. So thus we have constructed this polynomial, and now we can use this polynomial. So all we have to find is, so we have to find out f0, h is of course is evenly spaced, we know. So then we of course we have all the x0 points know, h is we know. So once we find out this difference for our difference table, delta f0, del square f0, when you have this difference table for any arbitrary x, we can use this polynomial to find out the behavior of the function. Let us take an example and see how this Newton forward difference interpolation can be implemented. For example, so this is the data set we are having. Where x we are having, how many points we are having, 7 points we are having, and this is all evenly spaced. You can check 0.2 is a difference, evenly spaced data, and we have this functional value, and we want to find out what is the value of the function at certain unknown x, certain x for which we don't have the data, 6.6. So let us see how to do it out. So what we do is, so this is the way we have plotted this function. So for corresponding to all the given values, we have plotted the function, and so we are going to form a first difference, that's our delta f. We are using forward difference. So this difference between these two, and that's what I have written here. So I construct the first difference, and then difference between these two, that's my del square f, and the difference between, I can keep on doing it to find out the difference up to the n. So this is this is 2, this is a 3, 4, 5, 6. So we have constructed the difference table like this. So and now if you see our interpolating polynomial, so the interpreting polynomial is something like this. All it needs is, of course, h is given, there's in this case h is equal to 0.2 and x0 is 6.5, that's also is known. So all we have to find out is del f0, del square f0, and keep on going, that is the top one, whatever these are the values. If we know all these values 1, 2, 3, 4, 5, 6, 7 del forward different values, then we can use this to find out the behavior of the function for any unknown x. For example, when you put up these values and calculate for 6.6, this is what you call 0.3125, and if you plot that point, this is what the unknown value, and this you can see this nicely follows the trend of other points, and this is how the interpolation is being Newton forward difference interpolation is performed. It is not necessary we have to always perform a forward difference, rather we can perform a backward difference also, and that also can be, we can construct the polynomial. There will be one polynomial, only one nth order polynomial, so will be passing through all the points. We can use the backward difference also to construct the same polynomial. So how we are going to do is, so in that case let me define a backward difference operator. So let me call it as nabla f of I will be equal to f of I minus f of I minus 1. So similarly then I can write del square of I will be equal to del f of I minus del f of I minus 1, and del cube of f of I will be equal to del square f of I minus del square of I minus 1, and you can keep going on until you get maybe certain k. I can do a k of f of I will be equal to k minus 1 f of I minus nabla of k minus 1 f of I minus 1. In the same fashion we will continue. So let me write down. So in this case let me take it as n. So backward, I am doing a backward difference. So backward difference means I am going to take the difference from the bottom side. So earlier we wrote everything in terms of del f0. Now we are going to find out that difference table what we constructed. Instead of taking the top one, we will take the bottom one. So what am I going to do? Let me write down delta f of n. So delta f of n will be equal to f of n minus f of n minus 1. So from here we can write f of n minus 1 will be equal to the same way. So delta, 1 minus nabla f of n. So we can do further. So nabla of f of n minus 1 will be equal to nabla, f of n minus 1 minus f of n minus 2. So this will give you f of n minus 2 will be 1 minus nabla of f of n minus 1, and when you put that when you substitute for f of n1 minus here, so what we are going to get is 1 minus del whole square of f of n. So we can keep on doing that, and finally what we are going to get is f of n minus k will be equal to 1 minus nabla to the power of k to f of 1. We'll proceed the same method how we were doing it earlier. Let me try to expand f of n minus k in terms of as a binomial series. So what am I going to do? We have f of n minus k, which is nothing but f of x of n minus k, and if I want to expand this in binomial series, what you are going to get is f of n. So since here it is minus, so what you are going to do, you get is minus del f of n by n 1 factorial into k, and second term will have become positive because del square will come out, del square f of n divided by 2 factorial into k minus 1, plus it's keep on going, and final term may be the nth term. We never know, it can be either positive or negative depending upon which the odd term or even term. So we will get del power n f of n divided by n factorial k into k minus 1, k minus 2, and it will be like before, k minus n minus 1. Correct? Yes. Fine. So now let us proceed the same way. So x of n minus k. X of n minus k will be x of n minus kh. Correct? Because that will be the from the n minus k. N minus k is a kth term from the n from bottom. So this will give me k equal to x of n minus k minus x of n divided by correct, x of n minus k, sorry, this will give us sorry, this is x of n minus k here. So this will give us k equal to what here, x of n minus k divided by h. So let us substitute this k here the same way. What happened? We will substitute this k and take all the number of h terms outside and take it right commonly outside. So f of n minus k will be f of n minus nabla of f of n by h1 factorial into, this will be x of n minus x of n minus k plus nabla square f of n divided by h square 2 factorial, and this is going to be x of n minus x of n minus k, and the next term will be x of n minus x of n minus k minus h, the same way what you had done earlier. So plus, go on, then it will be, next will be minus, sorry, this will be minus, sorry, next term will be minus, and then go on, and finally we are going to get plus or minus of this value, this portion, that is del power n f of n by, so again from here we can basically have n k values. I can take all the n h values outside, so we are going to become h power n factorial, and k will be xn minus xn minus xn minus x of n minus k, and the next term will be x of n minus x of n minus k minus h, and then it go on, and finally what you are going to get is x of n minus x of n minus k minus n minus 1 times of h. So what we can do is, and so this is a plus minus, keeps alternating. So we can express the whole term in positive as a series of positive terms by taking one minus from here. So what we are going to do, so I take one minus outside here, so this becomes plus and this will become x of n minus k minus n minus k minus x of n. So here, even though if I take, I can same way I can write this here, and what we will have is this also will become x of n minus k minus x of n into x of n minus k minus x of n plus h, correct? And then that way I can make every term as positive, and finally this also will become positive, because depending upon the term I can take equally the numbers outside. So this is going to become x of n minus k minus x of n, and this will also become x of n minus k minus x of n plus h, because we are taking one minus outside. N minus k minus x of n plus h. So, and this will be x of n minus k plus x of n, and this will be plus. Again, if you see here, depending upon what is our n minus k, if n minus k is equal to 0, so you will see all the, so n minus k equal to n, for example, if you take n minus k equal to n, so all the other terms will become 0, we get f of n. So when you get n minus k, if you write n minus k equal to n minus 1, you will see what you are going to get when you do this, when you expand this and put up these forward difference operations, what we are having, what we will get is, then it will become f of n minus k. When x becomes n minus k, it also becomes f of n minus k. So that's what this expression is telling us. So what it says is, again the same way, this is a function which describes all this data, the entire data. So what am I going to do? Instead of x of n minus k, so I will write this as f of x, and replace all your n minus k as x. So then we got our polynomial which passes through all the points and which can be used to estimate our estimate the function at the unknown variable x. So this is what we do it. So we can use Newton's forward difference or the backward difference to find out the polynomial which passes through all the points. The only requirement is your data point has to be evenly spaced. The interpolated value may not be correct, because the reason is, what we have done is we are expressing the behavior of this function f of x using a polynomial of certain degree n, but our function may not be able to express as a polynomial of degree n. So in that cases, your interpreting function is not correct, so it may give rise to error. So let us try to find out what should be the typical magnitude of the error. What you can do is, so let us say, for example, let f of x be the behavior of the actual behavior of the system, which is described. We don't know this function is, which we are representing as a polynomial. So let us try to find where, let us write that this x will be closer to any of these x values what are given. So we will write it as f of some xi, which is any of the x values, plus some epsilon. So where epsilon is a difference between them. So if you see, what is the maximum value of this epsilon will be h, because that's the difference between them. So if and when we want to calculate the error, we want to always find out the maximum error. So let me write this as maximum value, possible maximum value, that is xi plus h. So now let us expand this as a Taylor series. F of xi plus h will be equal to f of xi plus h divided by 1 factorial into f prime of xi plus h squared divided by 2 factorial f double prime of xi plus keep on going, and maybe what happened, we may have certain something like that, plus h power n, maybe nth term, n factorial f of nth derivative at x equal to xi plus on. Now if you see, the moment if we express this function as a nth degree polynomial, any derivative f of n plus 1th derivative will become 0. So after this term, by approximating this function as a polynomial of degree n, what we are happening is we are missing all the terms beyond this. They all vanishes. But for a real for an actual function, those terms may be still be finite and valid. So by approximating the polynomial, we are omitting all the other terms. So that forms the error. So let me write down the first term, which we see to be for smaller h, that is the it will be a decreasing function, decreasing value. So let us take out the next term which we omitted is h power n plus 1 factorial into f of n plus 1th derivative of, say, some xi. Let's go on. So this gives us typically the order of the error what we have in our calculation. So we will remove these portions and I am going to write this term as the error. So our error will be typically the order of, say, let me don't call it xi, let me take some some value zeta. Zeta can be any x in between the range where this derivative is maximum. Because when you are finding the error, we have to always put up the maximum value. So I won't call it as xi, where zeta is any value in between for which the n plus 1 derivative is maximum. I will use that, and that gives you the typical error in the interpolation.